Okay, so get ready. Because today we are going deep into some pretty crazy physics, even for people who are into this stuff. We're talking about this paper called "The Universe is Just Motion: The Biggest Scientific Blind Spot Ever." Even the title is a lot, right?
Yeah, no kidding. It really makes you want to know more. And it says right there, like right up front, that we need to rethink how we see everything.
Yeah, like the whole universe isn't made of, forces or whatever, but it is motion.
Right.
It's not just made of motion; it is motion at its core. Like all the way from the tiniest particles to those huge galaxies, it's all just motion arranged in different ways.
Yeah, and the cool thing is how they connect that huge idea to something we do every day. Seeing. They break down how our eyes take in light, which they say is just motion, like carrying information, and then how our brains see those different like speeds of motion as colors.
Okay, wait, hold on. So like when I look at a red apple, I'm actually seeing how fast something is moving. That's kind of wild.
That's the idea. And even depth perception, that thing we just do without thinking about it. That's them saying our brains are like tracking how the motion from our two eyes syncs up. So like right away, they're trying to make this crazy idea make sense, using something we all know.
It's like they're saying, hey, you know how you see the world? Well, that's proof that everything is motion. But they don't stop there, do they?
No, they don't. They take this idea about motion being organized and use it for the whole universe. Gravity, electromagnetism, even like what mass and time are. The paper says those are all just motion but acting different.
Hold on. Are you saying that the reason I'm like stuck to the ground isn't because of some force pulling me down, but it's like motion doing something?
That's exactly it. Instead of gravity being this force from far away, this way of thinking says it's about things, like syncing their motions together. That feeling of weight, that's just your body like fighting that syncing up.
So I'm not being pulled down, but I'm being like synced down.
Yeah.
To think about that one.
It does take some getting used to, yeah. But then the paper goes even further and says that even the Big Bang, the thing that supposedly started everything, wasn't like stuff exploding. It was like motion suddenly becoming organized. They call it the big motion event.
Okay, now you're really messing with me. So instead of an explosion of, stuff, it's like motion suddenly got like organized.
Mm-hmm.
How do they even begin to explain that?
Okay, imagine like a perfectly still pond. Then someone drops a pebble in, and all of a sudden there's ripples and waves, like bouncing around and making patterns. The paper's saying that the big motion event was like that. Quiet motion becoming all these ripples that made, well, everything.
So stars and planets and galaxies, even us, we're all just ripples in the universe's motion pond.
That's the theory. And it really changes how we think about how the universe works. The paper's saying that physics messed up by looking at all these forces and tiny particles separately instead of seeing how it's all just motion underneath.
So it's like they're not just adding to what we know. They're saying we need a whole new way to look at it. But do they have anything to back up such a big claim?
That's where things get really interesting. They ran like computer simulations based on just motion. And they say they were able to make some of the most basic things in physics happen, starting with gravity.
Wait, they like simulated gravity without using any of the normal physics stuff? How's that even possible?
Instead of a pulling force, they made the things in the simulation interact by syncing up their motion. And guess what? They got orbits, just like in our solar system.
You mean like planets aren't being pulled by the sun's gravity, but they are like syncing their movements with it?
Exactly. Think of it like dancers, like moving together perfectly. They're not pulled together, they're just moving in sync. The paper says gravity could be like that, but on a huge cosmic scale.
Okay, my brain is starting to hurt a little. But this is like really cool. And they didn't stop at gravity, right?
No, they didn't. They looked at electromagnetism too, and even quantum mechanics, and got some really interesting results. But I think that's a story for the next part of our deep dive.
Ooh, a cliffhanger. Looks like we'll have to wait for more.
Uh-huh.
All right, so last time we were talking about this wild idea that the universe isn't built on forces, but on motion. And they even like made simulations to show it, showing how gravity and orbits could just be like motion syncing up.
Yeah.
So where do we go from there?
Well, the paper doesn't just like change the basics. It goes on to look at some of the biggest mysteries in physics. Stuff like time travel and time dilation and all that weirdness in quantum mechanics.
Okay, so you're telling me they found a way to explain quantum physics just using motion? Because last I checked, quantum physics was, well, really confusing.
Confusing is like an understatement. But the paper says a lot of that confusion is because we're trying to like cram quantum physics into our usual way of thinking about the universe, with forces and stuff. They say it all makes way more sense when you think of it as motion adapting to different limits.
All right, let's start with a fun one. Time travel. Is it possible in this, motion-only universe? Because if it is, I've got a few things I need to go back and change.
You might want to hold off on building that time machine. The paper actually says time travel is impossible because in this way of thinking, time isn't really a thing.
Wait, what? You're saying time isn't real?
Mm-hmm.
But we can measure it, we experience it. It's definitely real when I'm late for something.
Think of it this way. We can, measure how long a table is, but that doesn't mean length is like a real thing floating around out there. It's just a way we describe like a feature of the table.
So they're saying time is kind of like length. It's a way we measure something, not like a place we can go to.
Exactly. What we think of as time is just us seeing changes in motion. Clocks tick not because time is flowing, but because, the stuff inside them is moving.
So no jumping in a time machine and going back to the past. Bummer.
Not in this universe. But the paper does give an explanation for another time thing that's confused scientists forever. Time dilation.
Right. That's that crazy idea where time slows down your huge objects or when you're moving super fast, like in that movie Interstellar, where they land on that planet near a black hole and time slows down for them, but back on Earth, years have passed.
So this framework says time dilation isn't time actually bending. It's about how motion syncing up changes in different situations. Imagine a bunch of synchronized swimmers. In a normal pool, they can move around and keep their movements in sync. But what if the pool was suddenly super thick, like swimming through honey?
I'm guessing their movements would slow down and it would be harder to stay synced up.
You got it. It's not that time is moving differently for them. It's that the motion in the pool is adapting to the new thickness. So like near a black hole or at super speeds, the motion adjusts to what's around it.
So a clock on a spaceship going really, really fast doesn't actually slow down. Its internal motion just syncs up differently compared to a clock on Earth.
Exactly. It's not that time itself is different. It's that the motion in those things is adjusting to different motion densities, you could say.
Okay, so no time travel, and time is an illusion. But what about quantum mechanics? Does this theory have anything to say about all that strangeness in the quantum world?
Oh, absolutely. The paper suggests that quantum mechanics, which can seem super random and full of paradoxes, actually makes more sense when you look at it through motion.
So no more spooky action at a distance or particles being in multiple places at the same time.
Well, not exactly. But those things, which seem so weird in our normal way of thinking about physics, might just be motion adapting to limits in ways we aren't used to seeing.
Okay, give me an example.
Let's take superposition, that idea that a particle can be in a bunch of states at the same time. It's how can something be here and there at the same time? The paper says it's not that particles magically exist in multiple realities. It's that their motion is adjusting to a bunch of limits all at once.
So instead of being in many places at once, it's more like their motion is spread out or taking a bunch of paths at the same time. Kind of like a river, branching out before coming back together.
That's a great analogy. And what about entanglement, that weird connection between particles that Einstein called spooky action at a distance? Remember those synchronized swimmers?
Yeah, they're still in that thick honey pool, right?
Exactly. Imagine that even though it's hard to move in the honey, they somehow stay perfectly in sync even when they're really far apart. That's kind of like entanglement. The particles aren't talking to each other instantly across huge distances. It's just that their motions were so perfectly matched from the start that they seem connected.
So it's less about spooky action and more about them already being in sync.
Right. And what about the observer effect, where just looking at something in the quantum world seems to change it? That one's always tripped me up.
Yeah, that's the one where it's just by looking at something, you change what it's doing. I have superpowers or something.
The paper says the observer effect isn't about our minds, collapsing wave functions. It's about the act of measuring something, which is a type of interaction, changing the limits of motion for the thing we are measuring. It's like if those swimmers were suddenly hit by a wave, their movements would get messed up, right?
So when we measure something really tiny, we're sending a wave that messes with its motion, and that's what makes it change.
Exactly. No need for mysterious explanation. It's all about how motion changes based on its surroundings.
Wow, so maybe quantum mechanics isn't so weird after all. It's just motion doing its thing. Right. So if this theory is right and everything really is motion, does that mean there's no need for, the multiverse? That idea of tons of parallel
You
universes.
got it. That's exactly what the paper says. That whole idea of a multiverse with infinite universes branching off every time something happens in the quantum world becomes kind of pointless if all that quantum stuff is just motion adapting to limits.
So no infinite realities, just one universe with motion constantly changing and adapting.
That's what they're proposing. And it goes even further, addressing that big idea about the heat death of the universe.
Oh, yeah, that depressing idea that, like, all the stars will burn out and everything will just freeze and the universe will end in this, like, cold, dark, empty place.
Definitely not a fun thought. But the paper offers a different way to look at it. It says that that whole heat death thing is based on the idea that energy runs out eventually. But if everything is motion, and motion can't be created or destroyed, just moved around, then the universe doesn't really run out of steam.
So instead of everything stopping completely, it's more like a constant shuffling around of motion.
Exactly. What we might think is the end, the heat death, could just be like the universe shifting to a new balance of motion.
Okay, so no time travel. Time is an illusion. Quantum mechanics is just motion, no multiverse, and no heat death. This theory is really flipping everything we know about the universe on its head.
And we're not even done yet. The paper goes on to explore all the amazing things we could do if we could understand and control motion itself.
Now, that's a cliffhanger. I guess we'll have to wait until the next part of our deep dive to find out what those are. Okay, so we've really gone deep into this idea that the universe is, like, at its heart, just motion. We've talked about how time travel isn't real and how time itself is kind of an illusion. And we even looked at all that weirdness in quantum mechanics all through this new way of thinking. But I got to ask, where does all of this take us? What does a motion-based future, even look like?
That's what's really exciting. The paper, paints this picture of a future where understanding motion changes, not just science, but, technology, medicine, maybe even how we understand consciousness itself.
Okay, you've got my attention. Hit me with the good stuff. What kind of crazy tech could we make if we figured out how to, control motion?
Okay, so first off, imagine physics not being all these separate forces and laws, but one unified system, all based on motion. No more random equations for gravity or electromagnetism, just the elegant laws of motion syncing up and lining up, controlling everything.
So physics would be, simpler, more elegant. That would definitely make those old physics textbooks easier to swallow. But beyond that, what about actual technology?
Think about it. If gravity is really about motion syncing up, like the paper says, could we invent things to control that? Imagine making artificial gravity or even anti-gravity.
Hold on, we got talking flying cars here.
Yeah.
Because I am so in. But wouldn't messing with gravity like that be, well, kind of dangerous? What if we accidentally made a black hole in the middle of, downtown somewhere?
That's a good point. Any new technology comes with risks. And yeah, using motion like that would be no different. But think about the good stuff too. Space travel without those huge rockets, buildings that float, new ways to get around.
Okay, I get it. So gravity control is on the table. What else? What about energy? Could we use this universal motion to solve all our energy problems?
That's one of the most interesting ideas. Imagine getting energy not by burning stuff or splitting atoms, but by using the motion that's already everywhere in the universe.
Now, that's what I call clean energy. No more pollution, no more fighting over oil. We would be swimming in clean energy.
Exactly. And the paper even says this way of thinking could totally change artificial intelligence. Imagine AI that processes information not as, ones and zeros, but as organized motion, just like how our brains work.
AI that thinks more like humans? That's kind of freaky and super cool at the same time. Wouldn't that mean AI could, actually become conscious?
That's a question that's going to get more important as AI gets smarter. If consciousness really is just a complicated pattern of motion, like the paper says, then making that pattern in a machine could have some side effects we didn't plan for.
It's like we're talking about making a new kind of life.
Yeah.
But besides AI, are there any applications that could, help us humans directly?
The paper even talks about how we might use motion to heal people and help them live longer by changing motion at the cellular level.
Wait, so we could use motion to fix damaged cells, slow down aging, maybe even reverse it? That sounds almost too good to be true.
It's definitely, still just an idea. But if this whole framework is right, we might be able to target the specific ways that cells move when they age or get sick and maybe resync them to a healthier state.
Now, that is seriously mind-blowing. We've gone from saying time travel is impossible to maybe reversing aging, all in one conversation.
And it all comes from that simple but powerful idea that the universe is basically just motion.
It's like a total change in how we see things.
Mm-hmm.
So if this theory is right, physics, chemistry, biology, neuroscience, they all become like parts of the same thing.
Right.
Studying different aspects of motion at different sizes.
That's right. Everything connected, a whole symphony of motion from the smallest particles to the entire universe.
We started this deep dive looking at a theory that at first sounds like something out of science fiction.
Yeah.
But the more we've dug into it, the more it really makes you think.
It makes us question everything we thought we knew about reality, and it opens up a whole universe of possibilities. Some are exciting, and some are maybe a little scary.
So as we wrap up this crazy, mind-bending trip, we'll leave you with this one last thought. If everything really is motion, what does that mean for you? What does it mean for how you see the world, for your place in this huge cosmic dance? Keep asking those questions, keep an open mind, and never stop being amazed by this universe that's always moving and changing.
Welcome to this deep dive. And, well, this one is going to be interesting. Today we're diving into a theory that says everything in the universe, it's all about motion. Not forces, not particles, but motion.
It's definitely a fascinating idea, right? We're so used to thinking about the universe, in terms of those forces and particles. But this paper, the universe is just motion. The biggest scientific blind spot ever argues that those might just be convenient labels we put on something much more fundamental.
But you mean like gravity, electromagnetism, even like what makes up atoms? It's all just motion.
That's the gist.
Yeah.
The paper really goes deep into how this motion-based framework could explain it all, from like the Big Bang to how those tiny particles behave. And it's not just some like wild speculation either. It's got computer simulations backing it up, logical arguments, and even real-world examples.
Okay, I'll bite. I'm intrigued. But I've got to say, I'm pretty skeptical. How can something as complex as like the whole universe be boiled down to just motion?
Well, let's think about it this way. Even our senses, they're just interpreting motion data.
Yeah.
Light, for example. It's just structured motion being transferred. Right. Colors, they're different frequencies of motion. And even our depth perception comes from our brains tracking the synchronized motion of our eyes.
Wow. I never thought about it like that. So basically, how we experience the world is already fundamentally based on motion.
Exactly. And when you zoom out to the bigger picture, this idea of a universe built on motion, it starts to make even more sense. Think about magnets for a second.
Okay.
They work because the electrons are all aligned in their motion.
Right.
So the thought is that maybe gravity is kind of similar, but on a much larger scale, where it's mass synchronizing motion instead of just electrons.
Okay, I see where you're going with this, but like with gravity, I can feel it, right? It feels like there's this force pulling me down to Earth.
I get your skepticism.
Yeah.
It's tough to imagine it any other way. We're so used to thinking of gravity as this force. But what if, instead of a force, gravity is actually a result of synchronized motion on a massive scale? Imagine like a flock of birds all flying in formation. Each bird is moving individually, but their collective motion creates a pattern, right? So what if objects with mass are kind of like those birds? They're somehow synchronizing their motion and creating this effect that we feel as gravity.
So you're saying a planet like Earth has this really complex and stable motion pattern, and my body's motion wants to sync up with that, which is why I feel pulled towards it.
That's the basic idea. And the more massive an object is, the more it influences the motion of everything around it.
Okay, that's starting to make sense. But if gravity isn't a force, then what about the Big Bang? How does a motion-based universe even begin?
Well, the paper calls it the big motion event. Instead of an explosion, it describes a state of pure motion equilibrium that for whatever reason got disrupted, leading to the formation of structured motion patterns, what we traditionally call particles and energy.
So instead of everything exploding outwards from a single point, it's more like everything was already moving, and then something happened to make that motion organize itself into the structures we see today.
Yeah. That's a good way to visualize it. And from there, it's all about how motion adapts to constraints. Think of like water flowing downhill. It's constantly adapting its motion to the shape of the terrain, right?
So galaxies, stars, planets, even us, we're all just structured motion adapting to the constraints of the universe. That's a pretty wild thought.
It is, isn't it? And the paper argues that this framework could actually help us solve some of the biggest mysteries in physics, things that traditional models really struggle with.
Like what? Give me an example.
Well, for instance, physicists have been searching for decades for something called a graviton. It's a hypothetical particle that they think carries the force of gravity, but they haven't found it.
And if this theory is right, they never will, because there is no graviton.
Exactly. The paper suggests that we've been looking for the wrong thing. because we've been thinking about gravity in the wrong way.
So instead of particles pulling things together, it's more about how objects synchronize their motion based on their mass.
Precisely. And this leads to some pretty big implications. Because if gravity isn't a force, but an emergent property of motion, then the way we think about things like space and time might need some serious rethinking.
I'm starting to see how this could get really mind-bending.
Oh, it definitely does.
Yeah.
And that's where things get really interesting, because the paper goes on to explain how a motion-based framework could change how we understand everything, from time travel to the ultimate fate of the universe.
Well, I'm definitely hooked. Tell me more.
So where do we even go from here with this theory?
Well, the source material doesn't just stop at describing this framework. It goes on to provide evidence and explores the potential implications of this motion-based view of reality. There's a whole section called the proof. What's in there?
This section dives into these computer simulations they ran, comparing their motion-based model to traditional physics. And the results, well, at least according to the source, are pretty compelling. They claim to have successfully simulated a range of phenomena, from gravity to electromagnetism to quantum mechanics, all without resorting to traditional forces or particles.
So they're saying their simulations show that these forces that we've always assumed are fundamental might actually be emergent properties of how motion interacts at different scales.
That's what they're suggesting.
Yeah.
For example, their gravity simulations show that objects naturally adapt their motion based on the motion density around them.
Hold on, motion density. Can you unpack that a bit?
Okay, think of it like this. Imagine like a crowded room versus an empty one. In the crowded room, it's harder to move around freely because there are more people, more motion packed into the same space. That's higher motion density.
Okay, so in the context of gravity, a more massive object like a planet would have a higher motion density than, say, a pebble.
Exactly. And according to their simulation, objects with higher motion density influence the motion of objects around them, creating the effect we experience as gravity.
So no mysterious force pulling things together, just a natural consequence of motion trying to find a balance. That's pretty elegant, actually.
That's one way to put it.
Yeah.
The source also simulated electromagnetism. But instead of relying on positive and negative charges attracting or repelling each other, they modeled it as motion synchronization and alignment.
So instead of opposite charges attracting, it's more about their motion patterns syncing up.
That's the idea. They claim their simulation showed attraction and repulsion emerging from how motion aligns or becomes misaligned between particles.
Yeah.
They even simulated one of the most famous quantum mechanics experiments, the double-slit experiment. Are you familiar with that one?
Vaguely, yeah. It's the one where light acts like both a wave and a particle, right?
Yes. It's a classic demonstration of wave-particle duality, a core concept in quantum mechanics. But instead of invoking wave functions and probabilities, their simulations showed the same results using only motion synchronization and constraints.
So no more wave-particle duality, just different motion patterns emerging depending on the setup of the experiment.
That's what their simulations suggest. They argue that a lot of the weirdness we associate with quantum mechanics might just be a result of our limited understanding of how motion behaves at the most fundamental level.
Okay, so their simulations seem to support this motion-based framework, but the source material goes further than that, right? They actually kind of take aim at traditional physics models, pointing out their flaws and inconsistencies.
You're right. They argue that traditional models, while they've been successful in explaining many aspects of the universe, still have some major holes. For example, the standard model of particle physics requires a whole zoo of particles with specific properties, but it doesn't explain why those particles exist or why they have those properties.
And if this source is right, it's because we've been trying to define fundamental building blocks, when really it's all just motion at different levels of complexity.
That's a good way to summarize it. Yeah. They even challenge our understanding of time. We're so used to thinking of time as this linear progression. But the source argues that time as a fundamental entity doesn't actually exist.
Wait, so they're saying time isn't real? That's a pretty radical idea.
It is. But their argument is that we never actually measure time directly. We only measure changes in motion. Think about any kind of clock. It's always tracking some form of motion, whether it's a pendulum swinging or atoms vibrating.
So clocks tick because things move, not because time itself is flowing.
Precisely. And they argue that the phenomenon of time dilation, where clocks run at different rates depending on their motion or gravity, further supports the idea that time is tied to motion, not the other way around.
So instead of time being warped by gravity or speed, it's more like the motion of the clock is adapting to those conditions, and we interpret that as time dilation.
That's what the source proposes. Even the concept of mass, which we tend to think of as a fundamental property of matter, is redefined in this framework.
How so?
Well, we know that mass isn't actually constant. It changes with velocity. That's what relativistic mass is all about. But if mass were truly fundamental, there'd be no reason for it to change based on motion.
So they're saying mass is more about resistance to changes in motion rather than a fixed property.
Exactly. They argue that mass is an emergent property of how much a system's motion resists being redistributed.
It seems like everything comes back to motion in this framework. So where does this all lead? If this theory is right, what does it mean for our understanding of the universe?
That's where things get really interesting, because the source material delves into some of the biggest mysteries in physics and explores how a motion-based perspective could offer new solutions. And perhaps even more excitingly, it explores the potential technological breakthroughs this theory could unlock.
Now you're speaking my language. This is where we separate the science fiction from the science fact. Let's dive into those implications. Okay, so we've explored this radical idea that the universe is built on motion, not forces or particles. And we've seen how this framework could maybe explain things like gravity, electromagnetism, even quantum mechanics in new ways. But where does it all go from here? What are the big implications of this theory?
Well, the source material, it dives into some pretty mind-blowing possibilities. One that's really intriguing is the idea that time travel as we usually think of it might actually be impossible.
Wait, hold on. So no hopping into a DeLorean going back to 1955?
Not if this theory is right. Because remember, the source argues that time itself isn't this fundamental dimension. What we experience as time is just our way of measuring changes in motion.
So if there's no real timeline to travel through, time travel is kind of pointless.
Exactly. And it also provides a new way of thinking about the multiverse.
Yeah.
That idea that every quantum measurement creates a whole new universe with a different outcome.
Yeah, that one always felt a bit out there to me. Infinite universes, really.
The source actually calls the multiverse totally unnecessary. If quantum mechanics is just about motion adapting to constraints, then there's no need for all those branching realities. Just one universe, and it's all motion unfolding according to these fundamental rules.
So a simpler, more elegant solution. I like it. But what about the fate of the universe? Right now the thinking is that everything will eventually end in this cold, dark state called heat death. Does this theory have anything different to say about that?
The source tackles this head on. It argues that the concept of heat death comes from misunderstanding motion. If motion can never be truly destroyed, only transformed, then the universe can never really run out of energy.
So instead of a bleak ending, it's more like an ongoing transformation, a constant dance of motion rearranging itself.
That's a beautiful way to put it. But honestly, the most exciting implications of this theory might be the tech breakthroughs it could lead to.
And now you're talking my language. Give me some examples.
The source envisions things like gravity control, new energy sources based on harnessing motion itself, and even motion-optimized AI.
Wait, gravity control? Are we talking anti-gravity devices, flying cars?
It might sound like sci-fi, but if we can really understand how mass and motion work together, manipulating gravity might not be so crazy. Imagine vehicles that don't need wheels, buildings that defy gravity, or even using gravity to create clean energy.
That would be revolutionary. And what about those new energy sources? How would they even work?
Imagine if instead of burning fossil fuels or splitting atoms, we could tap into the inherent motion that's all around us. Capturing energy from earthquakes, ocean currents, even the tiny motions in our own bodies.
That'd be a total game changer. And motion-optimized AI, what does that even mean?
It means building AI systems that process info as structured motion. Just like how our brains seem to work, this could create AI that's way more efficient and adaptable than anything we have now.
Sounds like this theory could completely revolutionize not just how we see the universe, but our whole tech landscape.
The source even suggests that motion-based tech could change healthcare. Using structured motion to fix damaged tissues and organs. Maybe even extend lifespans and enhance what humans can do.
Wow, if this theory is right, it's not just a new way of looking at the universe, it's a roadmap to a totally different future.
It is. And even if this theory doesn't turn out to be the answer to everything, it definitely makes us rethink what we thought we knew and explore new possibilities.
It reminds us that we're really just starting to understand how the universe actually works. There's so much more out there to discover. And who knows what incredible breakthroughs are waiting for us just around the corner.
This deep dive has really only scratched the surface. I'd encourage you to check out the source material and see where it takes you. Who knows? Maybe you'll be the one to make the next big discovery about the universe and its amazing dance of motion.
And that brings us to the end of this deep dive. We hope you enjoyed exploring this thought-provoking idea. Until next time, keep questioning, keep exploring, and never stop being curious about this incredible universe we live in.